we are going to be talking about current division. In electrical engineering, oftentimes you end up with a circuit that has a current source and two parallel resistors. Because of that, people came up with the idea of current division, so that way they could directly relate I1 or I2 to the resistors and the input current. So in this video, I'm going to derive the relationship for I1 and I2 in terms of the other circuit parameters, so that way you can see where the current divider equation came from. Then we'll plug in some values and see how to use it in practice. In order to derive that relationship, I need to do circuit analysis, and I usually start by labeling my component currents, but in this case, I1, I1, and I2 already have labels, so I can move on to labeling my node voltages, and for this circuit we only have two. I have my ground node, and we can call this node V1. So the next step is I have to write KCL, and we can write KCL at V1, and I'm going to write that the currents that are entering the node are equal to the currents that are leaving the node. Now we have I in, which is pointing towards the blue region, and that's going to be equal to the currents that are pointing away, and that will be I1 plus I2. The next thing I'm going to do is write the equations for my components. And in this case, I have two components I have to write the equation for, and that's going to be two Ohm's law equations for R1 and R2. Beginning with R1, we can write that I1 is equal to V1 minus 0 divided by R1, and we have that I2 is equal to V1 minus 0 divided by R2. Now that I have these three equations, my goal is to define I1 and I2 in terms of the resistances and the input current. So I'm going to plug in my I1 and my I2 equations into my KCL, and that way I can get rid of V1. We'll have that I in is equal to V1 over R1 plus V1 over R2. So I'm trying to solve for V1. So turning this into one fraction, we have that I in is equal to V1 R2 plus V1 R1. So now we can factor out our V1s and divide both sides by this big fraction. And that'll give us I in multiplied by R1 times R2 divided by R1 plus R2 is going to be equal to V1. Now that I have a value of V1 in terms of my resistances and my input current, all I have to do is plug in that definition of V1 in my resistor equations. And then I'll have an equation that relates I1 and I2 to the circuit parameters. Starting with I1, we can say that I in R1 R2 divided by R1 plus R2 multiplied by 1 over R1. And what happens here is that the R1 cancels with this R1. And this gives us the final relationship that I1 is equal to I in multiplied by R2 divided by R1 plus R2. Similarly, we can say that I2 equals I in multiplied by R1 divided by R1 plus R2. And these are the current division equations. So let's plug in some values. Let's make this 10 amps, let's make this 3 ohms, and let's make this 7 ohms. That would give us that I1 is equal to I in, which is 10, which in this case is going to be the opposite resistor, so this is going to be multiplied by 7, divided by R1 plus R2, so that's 3 plus 7, and that is going to give us a value of 7 amps. Moving on to I2, this is going to be our input current, 10, multiplied by R1, the opposite resistor, multiplied by 3, divided by R1 plus R2, so 3 plus 7, and that is going to give us 3 amps. And if you add 3 amps plus 7 amps, you get 10 amps. And that's a good sanity check to make sure that the KCL still works. And that is all there is to current divider. If you enjoyed this video or found it helpful, please like and subscribe. I'll see you next time.